Why did Einstein reject quantum mechanics? Because the goal of physics is twofold. We want to make predictions and be able to calculate results based off of those predictions. And two, we want to understand what's really going on physically. Quantum mechanics only accomplishes one of those things. And it was that way in his day, and it's that way to this very day. Because when we solve the Schrodinger equation, we can figure out what possible energies the system will go to. But when we make a measurement, it's only one of those possible energies with some probability. And we don't know why that it's random. We also don't know why the system, if we leave it alone, goes back into a superposition and then can be a different energy the next time we measure it. We have no equation for that either. Today I'm going to talk about an apparent paradox in relativity and its resolution. That's right, today we're going to talk about what is the length of a photon. So here we have the formula for length contraction. L0 is the length of the object in its moving frame. L is the length of the object as measured by a person at rest. As you can see here, the formula will show a shortened length for the object if it's measured in a rest frame, because the original length L0 is multiplied by that factor in the square root, so it's less than 1. But a photon goes at velocity of c. Having a look at this formula again, that would give 0 for the term inside the square root. A length of dun 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 0? How could a photon have 0 length? It doesn't. This formula doesn't work for a photon because the photon has no reference frame where it's at rest. So this is only valid for massive particles. Okay, so I wanted to sort of illustrate this problem of quantum mechanics and relativity. So I'm going to start with an electron. So here we have a single solitary electron. According to a classical theory like general relativity, we could picture this electron as a solid object, even if it's very tiny. This is how the electron was viewed in the early 20th century. If this is the correct picture of an electron, the gravitational field associated with the electron should look something like this. As you can see here, the electron's mass is sort of bending the space and time around it. These coordinate grids could just represent measurements, and so you can see that there's a gravitational field associated with this electron. But this was shown to be wrong. The electron does not have a definite position. At any moment in time, it has a probability cloud associated with it. You can see how ridiculous this definite coordinate system looks when superimposed on this probability cloud. Another issue where quantum mechanics doesn't agree with relativity is in the spin of a particle. Because if the electron was spinning in a classical sense, it would create this sort of frame dragging effect that you can see here in this image. But the issue is, spin is not a classical spinning in the normal sense. In fact, you have to actually rotate twice around to end up in the same spot that you're located. So a 360-degree rotation, you do not end up in the same spot as where you started, like you would in classical space. This is yet another disagreement between quantum mechanics and general relativity that is still yet to be resolved. So far, we've seen that if we don't measure an electron, it can go through both holes at the same time, or it seems like it does, and interferes with itself like it's a wave. But if we measure it at either of these points, it doesn't obey this distribution at all. It'll only land either here or here, as if it went through one of the holes. Scientists are extremely divided about this problem because it seems like there's no instrument that we can invent that can determine what's actually going on. Because if we measure it, it seems like we destroy its behavior itself. And this kind of non-local behavior where the electron seems to be interfering with itself at different points is what led Einstein to reject quantum mechanics and think that the Schrodinger equation was incomplete.